We're going to get rolling. This is Big Tech for those of you that are new to this show, biologic internet gateway technology. And what this really is all about is this transition into the new normal that will emerge on the outside of this fourth industrial revolution and the Great Reset. And what it is the fusion of biology and the digital space all into one, where they're going to merge life with the internet so that everything is going to be connected. That's the underpinning essence of this show. That being said, we are on episode 121. Technically, we've done way more than 121 episodes, but some of them are replays and more for fun. And the stuff that's really structured, I'm trying to keep in some type of a numerical order. There's an archive. If you want to go look at these notes, go to psb.com and you can find Big Tech notes and archives. It's also listed here in the description of the show, right? Right here under Technologic Mind Control, TMC, right? Technologic Mind Control. And if you click that hyperlink, it will take you to the archive notes where you can get everything. You get all the notes that I've compiled from episode 1 up until now, and they're linked in groups of 10, and they're all here. And it's all open source information. I'm not charging for this. Good luck. I encourage you to read the hell out of it because it'll blow your mind. All that said, let's get going. If you have not gone to earthpulse.com, I encourage you to go to earthpulse.com. Earthpulse.com is a website that is managed, run, content all from Dr. Nick Begich. And he's doing a Hidden Monks Masterclass 10-hour live stream here pretty quick. I think it's the 1st of April. And Dr. Nick Begich has been in this field of technology and how it is interlacing with the human mind for decades. Very, very, very well known in this field. Talk to the best and brightest. This website is way worth your time. We're going to look at some of the documents off of this website. It's time. I've seen them for a while, and every time I go back and look at them, they make more sense. And I'll show you here if and when they'll load. Let's might as well get these guys started while we're waiting. So I want to show you a little bit of this tech, and then we're going to come back to it. It's important to understand back in the early 2000s what DARPA was looking at, because it's now in the public space. And you can tell by the way that this document has been formatted that this was a long time ago. The documents that come out for this kind of stuff are much prettier now than they were back then. And this is interdisciplinary research, Office of Naval Research, interdisciplinary research examples in optics, basically, naval research. And they talk about OLEDs, right? So new phones, you got an OLED screen. Yeah, well, they were looking at this stuff for fighter pilots and airplanes and stuff back in the early 2000s. And now it's on your cell phone. Nano channel for glass and neural interfaces. So this is a nano channel glass. In this case, they're talking about neural interface, but nanochannel glass also functions in screens. And we're going to look at this a little bit because I want to visually illustrate for you how they're going to be able to do things like prism light. And you ask me, like, what are you talking about with prisming light, right? And I'll show you here. I didn't want to overload my computer. Prisming light will do things like project a dot pattern. And projecting a dot pattern would be something like this. Face ID on your cell phone, right? It's projecting dot pattern. And they do that with prisms and with different ways to what they call beam splitting the light. And this is what we're going to look at a high level tonight. And so I want to give you some good visual representation of just exactly what's going on your phone, right? So this is a flat component at this point that is the Face ID hardware that it's able to emit laser beams and duplicate and replicate laser beams to create upwards of 30,000 dots on your face that are at power levels that don't blind you, but they're at power levels that are higher than what's needed, in my view, to stimulate nerves. And they use Vcsel diodes, amongst other things, but the focus that I looked at were Vcsel, vertical cavity surface emitting lasers. I'll say that again, vertical cavity surface emitting lasers that are put into your phone in a sleek form factor that project laser light out and map a three-dimensional environment. So we'll look a little bit at 3D mapping, but then we're going to look at how they use the stuff with biometrics. And this is what, when I was talking about nanochannel glass and that kind of stuff, look at this. So this is like a laser that goes into a substrate, if you will, and the beams, they split. And when we look at this nanochannel glass, it'll give you one example of how this could possibly be done. Keep in mind that this stuff was forecasted back in the early 2000s. So the material science and the technology and development and the manufacturing and all that stuff is likely much better now than what they were proposing back in the early 2000s. But it's to give you an idea of how small they can manufacture and do things like split light and replicate light and keep the same power levels, even though they're splitting the beam. Each of the independent beams have a significant amount of power, minimal power loss, which means that they're basically able to amplify the power. And that's kind of scary when you think about things like nerve stimulation, which we'll talk about a little bit. Pulsed laser versus electrical energy for peripheral nerve stimulation. And we're not going to read this whole document, but there are a few things in here that discuss being able to stimulate nerves and being able to pick a particular wavelength to penetrate a certain amount of tissue and then activate a particular component of the nerve. And when you think about a nerve in your arm that is responsible for sending signals all the way down to your hand, the whole nerve doesn't necessarily need to be stimulated. You can stimulate the nerve at the top, you can stimulate the nerve in the middle, you can stimulate the nerve at the bottom, the same nerve, and it activates different signals. It sends different signals. So the nerve bundles, nerve facile is what they're called. You can specifically target those things. And they're talking about working in centimeters in this document. They're talking about working in centimeters using a 2.12 micrometer pulse, or a wavelength, excuse me. And that's infrared. That's near infrared. It's the same frequency band, if you will, that they're using in things like an iPhone for Face ID. And what they do is they can tune this stuff and they can selectively interact with the depth of a particular nerve. And I want you to think about how deep into the tissue your facial nerves are. Your facial nerves. Are your facial nerves above the skull, or are they underneath the skull? And how far in past the skin do you need to go to start interacting with nerves? So we'll look at this a little bit if we have time. Just know that infrared light is a preferred frequency, preferred band, electromagnetic band to stimulate nerves. And it says that optical stimulation occurs at 0.4 joules, which is equivalent to 0.4 watts per centimeter squared. And what I'll show you in these patents is that the minimum power that they discuss, for transmitting these lasers is 0.5 watt. And I just showed you where it said 0.4 joules, which is that's 400 milliwatts, right? Can be enough energy absorbed into a nerve in order for it to stimulate, to create what they call a compound action potential, CMAP. And I'll search for you CMAP, and we will read what CMAP means. So measured responses include compound nerve and muscle action potentials. Compound nerve action potential, compound muscle action potential. So what I'm trying to show you circumstantially in a nutshell is that the power field density of something like this potentially has enough power when it's focused to start stimulating your facial nerves, let alone whatever it's doing directly in your brain and through your eyes with the pulsing that it does. We will look at some other topics, particularly in optogenetics, that discuss using things like infrared light to do a variety of things in your brain, like controlling behavior. So this is really this is the show in a nutshell. So I did my best to tell you in 10 minutes. Those of you that want to go to sleep, good night. Those of you that want to stick around and look at some of the detail, we're gonna start getting into the nitty gritty of it now that it looks like some of this stuff might be loaded. So let's look at military applications for this. This whole thing's about infrared light. So they were using this stuff for laser guided missiles and for defense mechanisms and basic directed energy applications for things like on airplanes, right? And it evolved from there. And now this stuff is all the way in your cell phone. And there's a couple pieces in here that I want to show you before we move forward. And I'm kind of scrolling through this fast, but it's simply to give you an idea of this is really how technology reaches the consumer space. It's this kind of stuff. So your OLED screen, organic light emitting materials and devices, they were looking at doing this way back then, early 2000s, right? For flexible heads-up displays, flexible materials that would be able to emit or basically display graphics. And it's useful, obviously, in for military applications, amongst other things, like in our case, using a cell phone. And they were working on this stuff way before we ever saw it. So they go into some specifics of what the project's looking for, voltages. None of it's really applicable unless you're really, really, really interested in it. And when I say not applicable, it's outside of the scope of what we're going to talk about. Accelerated research initiatives on nanostructured arrays. This is early 2000. Nanostructured arrays, meaning more than one on a substrate that work together in conjunction with each other to do cool things like phased array lasers, where they can steer them around and make like a light show and generate holograms. They can project with these systems, with what's in your phone, they can project pictures that then penetrate your body. They can project an image like a hologram, but not quite like a hologram. It's not that good yet. So they say. I can't tell you that or say that because I haven't personally read anything with what's just in a phone that can project a hologram. What it says is that it can project dots, it can project lines, it can project gradients of infrared, dark versus much brighter gradients. So think about like stripes, and then some of them being lighter and some of them being darker, in any combination. And then they say they can project pictures. Now, what is a picture? Could a picture be planar, meaning two-dimensional, or could a picture be three-dimensional? If a picture is three-dimensional and it's done with light, technically that's a hologram. So we're going to go through some of the hardware that will enable something like a hologram being projected into your brain. We're going to go through some of the hardware of how that actually works, the nuts and bolts of how that could possibly work. So nano fabrication and nanochannel glass. So this kind of stuff is in your phone, folks. That's how you get the beautiful, vivid colors and the high resolution is stuff like this. Nano-channeled glass that then have light emitting diodes, LEDs behind it that then are able to emit through the pores, the little nanopores in the glass, and that gives you your pixels. That's how you get your pixels. So it says they range from 200 nanometers to approximately 2 micrometers, and these are the the scope of what this project or program is looking for. Nanochannel glass. Microchannel glass is fabricated by bundling composite glass fibers. Check this out. So you've got your nanochannel glass, and what they're doing is they're literally putting together fibers, and fibers will direct. A fiber optic is basically a waveguide for light. So it'll keep light inside in the core, and it will steer it wherever it'll just go wherever the glass is. And so this kind of stuff is, look, they're looking at putting this stuff in like an eye for a neural prosthetic. Nanochannel glass technology for something in your eye. Imagine a contact lens to give you infrared vision or ultraviolet vision with a contact lens. Wouldn't that be pretty cool? Yeah. Well, this is kind of the stuff they're looking at. Nanochannel glass technology enables connections to millions of neurons. So you've got the chips and stuff they put in the brain, the little things that look like a comb, a Utah array, ECOG array. This is same general idea, only they're using glass so that they can transmit light. And we're going to look at optogenetics, and this allows for much higher spatial selectivity and probably greater temporal selectivity, which is time, because you're not using electricity anymore, you're using light, using pulses of light. And here's the benefits of it, right? You get real small electrodes, you get very good center to center spacing, a large array, which is greater than 1 centimeter, and no channel crosstalk, which is huge. This is a big difference between light and electricity. Electricity bleeds out, not as much as chemicals, right? Pharmaceuticals, but electricity does bleed out and light does not nearly at all comparatively to electricity. It will bleed out, but it's not. It functions completely differently. So here is the other piece we're going to look at a little bit later. Chemical and biological sensing using luminescent quantum dots. Quantum dots, biologically active luminescent materials conjugating luminescent semiconductor quantum dots with biological species. This is what you see here. You've got a quantum dot that has proteins or other genetic material or other biologic material that has been added to it so that it is bioavailable, so that the body understands it and likes it and absorbs it and integrates it. And chemical and biological detection using luminescent quantum dots, right? Luminescence is spectrally narrow, permits sensing of multiple species using many colors. It says a single ultraviolet laser, in this case, can excite emissions from quantum dots of every color. Quantum dots resist photo bleaching. We're going to look at upconverted nanoparticles, which are kind of the same thing. They're luminescent. They're technically quantum dots, but what they do is they use infrared light, and then they emit different colors of light when you shine infrared light on them. Talk about bioconjugation, which is just a real fancy word of saying that they're fusing synthetic technology, silicon technology, right? What we understand as silicon, even though they're made of different materials, with biology. So they're taking nature and the synthetic, and they're marrying them together. And in this case, they're showing an example of electrostatic attraction. And this has to do with ionic charge, positive and negative. And you have ionic bonds and covalent bonds, and this idea of positive and negative attracting and doing this stuff basically as biochemistry. And what you see here is a complete and total bioconjugate, where you've got positive and negative charges, you've got biologic material, proteins, DNA, enzymes, antibodies, could be liposomes, could be anything. That's all fused together with a quantum dot that is able to emit light. And we're going to move on. I'm going to come back to this nanochannel glass maybe later, so I think we'll leave it right here. Interactive neuronal and nanoelectronic nanophotonic circuit. So this is man and machine fusing, basically creating a brain-computer interface. Photonic superchip, where they're using light for computation on a computer chip. This is where we're going. And when they get this stuff good enough, this is how the quantum world will move into your phone, is with qubits that are done using light, because you don't necessarily have to have superconducting, supercooled substrate to be able to conduct quantum computation. If you use light, that can be done at room temperature. The quantum internet that is ongoing now uses fiber optic cables, as well as open air photon transmission, known as wireless or known as lasers, to create the quantum internet. So you don't have to have super cold environments for quantum networks, if you will. You might need it for advanced or current level quantum computing, but to move quantum information from point A to point B, very, very easy to do with light, because they've been doing it for 20 years or more at this point. And they've been doing it with wireless-based systems, either with light, lasers, or with other electromagnetic wavelengths and other parts of the spectrum, microwave, millimeter wave. Just think about satellite band, what satellite bands are out there currently in use, and ask yourself, can groups like the government and the military use those bands and encrypt them with quantum encryption? And if you've been around long enough, we have looked at quantum key distribution patents, that one in particular from Verizon that discusses transmitting quantum encryption keys using wireless transmission, using photons. So it talks about half spin systems, quantum computing, blah, blah, blah. And this is really where it's going. Neuroscience, brain science, biomicro info processor, right, as the main component, biologic and microprocessor, nanoelectronics and photonics, and neural network computer engineering, and neuroscience, with quantum networks and quantum computation above it all. What does the beast system look like, folks? So the Utah array I was talking about earlier, intercortical multi-electrode array, University of Utah, the Utah array, Bionic Technologies. This is a version of an ECOG array, electrocardiograph, something like that array. And this is, and they show you here a surgical implantation. They cut your head open, shove that fucker right in your brain and hook it up to a computer, and then start sending electrical impulses there that your brain interprets as neurocode so that you can run a prosthetic or type with your brain. That's the old way of doing it. There's much, much more sophisticated ways to do this now. So they show you the recording of it, this, that, and the other, and we're going to get into where they want it to go back in the early, see, this is 2000, the year 2000. So 21 years ago. Nanoelectronics, interactive probes coupled in neural and nano systems, and talk about in the body recordings, outside the body recordings, high spatial resolution, bioneural and nanoelectronic intersystem supercoupling. Ooh. So again, they're showing you all this nanotech. I mean, this is a 280 nanometer or 200 nanometers right here. And you've got an entire array of this stuff that is smaller than what you can basically see with the naked eye. You know, system design, bio, nano, electro interface. So they want to be able to read and write into the brain using these nanotubes. There's these nanochannel glass that we looked at a minute ago. And all this stuff will translate into quantum dots and or just with genetic manipulation. As the software gets better and better, they'll be able to use less and less to create the interface. So what they're looking at here is blue LEDs. Keep in mind, this was like 21 years ago. And here is the word of the day. Nomenclature of the day is a Vcsel, vertical cavity surface emitting laser for added spatial and temporal coherence. So blue LED arrays for cortical imaging. Now, blue is one of the first colors that they use for optogenetics. They used blue, and they quickly found red, and they had I think they have orange, if I'm not mistaken. They've got many now, but blue they used. It actually the brain responded. I think I just read this. I might show it to you. I think I've got the article up. The blue receptor was 10 times more responsive. So they liked using blue, and they used blue for a lot of the initial research. And this is an LED array and an electrical array that they would apply to your brain. And this is a 1.5 millimeter squared total area for this. A 32 by 32 element, individually matrixed, addressable array. So they have 1,024 LEDs in 1.5 millimeter that are all independently addressable, is what this thing is saying, that they want to put in your brain. DARPA, 20 years ago. They talk about the different issues, this, that, and the other. It says nanostructures or any brain-like computational architecture will build human-like computers. Human-like computers are good at intuition, association, plausible inferences. Hmm. Interesting stuff. So 20 years ago, Vcel arrays, nanochannel glass, looking at cortical modems, brain computer interface stuff, and DARPA Tech Symposium 2002. Brain machine interfacing, augmenting human performance. Behavior, brain technology, cell and tissue engineering, genomics and proteomics, bioinformatics. How much of this is relevant today? Your behavior, well, very relevant today, right? Especially with the censorship we're seeing and with the purging of the military and the scrutiny of social media to determine whether or not you're domestic extremist. Brain technology, well, that's a huge deal, right? That's all around us now, and it will become more and more publicized as time goes on. Cell and tissue engineering, we're undergoing a lot of that right now with the genetic therapies, if you will. Genomics, proteomics, same thing. Genetic therapies, these are all out in the public space now. Like people are drinking this stuff up from a proverbial fire hose at this point. Enhanced human performance. Okay, well, the opposite of that would be degraded human performance. But so it's a matter of how the tool is used. Enhanced system performance, protecting human assets, and this is the other half of this circle here. Biosilico interface, energy transduction, converting one form of energy into another, and then new materials. And 20 years ago, this was a big deal. It's still a big deal now. Material science has come a long way in the last 20 years, folks. A long, long way. Biocomputation. Now that's a word I bet Bill Gates probably gets a hard on for. Biocomputation, with his 2020-06-06-06 patent, where you use body mechanics and body heat and brain waves to collect cryptocurrency, courtesy of Microsoft. Anyway, biocomputation. Bill, if you're listening, don't have an accident, buddy. Biocomputation. Brain fundamentals, from pharmacology and physiology to learning and behavior, improving brain processing and retention of data. So they are looking at the human brain as a moldable, pliable piece of hard drive. Your brain is a hard drive. Bill Gates and others look at the human organism as a biological source that can do mechanical work, that the brain within that biological source that can do mechanical work is a moldable, pliable, uploadable, downloadable, erasable, modular system. Your brain, hard drive. Improving brain processing and retention of data, evaluating target sites and molecules for pharmacological interventions. And back in 2002, they were looking at this kind of stuff. Real-time two-way behavior communication with something like a mouse, where they would use a mouse, train it, and use it for something like search and rescue by jacking into its brain and controlling it and overriding it. Rats meet Tony. Tony looks like such a nice guy. Retinal prosthetic. Look, nanochannel glass as a retinal prosthetic. Chip output from a digital camera. Image recreation. So if you were blind and you got something like this pumped into your visual cortex from a nanochannel glass implant that maybe is in conjunction with some optogenetic gene therapy, to go from not being able to see at all to being able to see in grayscale that looks pixelated like this is pretty damn good. You would call that a significant sight restoration using a type of brain-machine interface. Control devices and machines with thought. Back in 2002, DARPA was looking at this kind of stuff. Deception detection. We're going to get into some of this too, where we look at patents that show infrared or various, there's a couple different categories of infrared: near, mid, and far infrared. And they are able to understand blood flow, heat dissipation, pore size to determine things like whether or not you're lying under stress, all kinds of things. They can determine all of that with infrared light. So main focus for tonight, folks, is this. Apple's Face ID biometric system works in the dark when your face is obscured by hats and beards. This is written in 2017. 2017. The new iPhone 10 Face ID, facial recognition system, replaces the Touch ID fingerprint sensor. Face ID is a new biometric system. A lot of questions about it. How does it scan your face? True depth front-facing camera on the iPhone 10 has multiple components. It has a dot projector. We'll look at those. More than 30,000 invisible dots on your face to map its structure. Dot map is read by an infrared camera. Structure of your face is relayed to the A11 bionic chip. That's an artificially intelligent chip, narrow artificial intelligence in the iPhone, and transformed into a mathematical model. The A11 bionic chip then compares your facial structure to the facial scan stored in your iPhone. Face ID in the dark. It has a flood illuminator. We'll look some about this. Infrared light that illuminates your face in the dark, so the dot map and the infrared camera can do their jobs. Can't really fool Face ID. It understands vein patterns. It understands subdermal structures. It understands which wavelengths are supposed to penetrate flesh. So if you're wearing a mask, it'll know. There's algorithms in there that go through all of that. It's super sophisticated. Same thing with this kind of stuff, beards and masks and all that. It'll show the stuff in the patents. I don't know if I highlighted it, but what they're getting at here is the iPhone will be able to map your face, and whatever's exposed. Let's say you had a mask up over your face, and all you had was the eyes and maybe part of the nose, right, and then a little bit of the forehead. Well, this is enough right here to identify you. There's enough information right here to identify you. They don't need the whole face. And they get into that where they look at like they're basically able to zoom with the lasers. And once they find what they're looking for, they can focus on a particular area and do more analysis. And they can selectively turn on and turn off any of the lasers. They're all addressable, and they can turn off some and crank up the power on the others, so they stay underneath the maximum power allowances, but they're still throwing out, a lot of power. They just turn off some of the lasers and apply that power to other lasers. So it's we're so far along in where we're going. It's pretty remarkable, quite frankly. Face ID and Apple Pay, and this is a critical piece to understand. You may not like Face ID. You may not use Face ID. You may think all of what I'm saying is complete and total bullshit. Just understand that the technology is refined enough, robust enough, and reliable enough to do things like authorize payments, to do things like authorize you to access your phone, to do things that you used to have to do with the fingerprint or a signature or showing ID. It's good enough for that. If it's good enough for banking, it's pretty much at a minimum standard, if you will, for being reliable and universally accepted. So that's really where we're at. And here's another piece: the neural engine. The Face ID is powered by a 2-core neural engine built into the A11 bionic chip. Keep in mind, this is a few generations ago. This is back in 2017. So it works in real time. It can process more than 6 billion operations per second. So that processor in your iPhone a few generations ago, iPhone, can process more than 6 billion operations per second. To train this neural engine, Apple used more than 1 billion facial images and created several neural networks. #privacy. So I'm going to show you this. We kind of looked at it before, but what I want to show you real quick is this dot pattern. And this stuff, it's in the iPhone, it's in the Xbox Connect, it's in, I have a phone that's got face login ID technology. I mean, and I don't have it's an Android phone, right? So it's everywhere. And this guy's showing you that this is coming out of an Xbox Connect. This technology is everywhere. It's not exclusive to Apple. But Apple has over 50% of the mobile market share. Therefore, it seems advantageous to look at their patents to understand how the mechanics of it works, at least how they're disclosing that it works. And then we can infer with circumstantial evidence what else it might possibly be able to do, which then is not exclusive to Apple. What that means is that if it's possible to do these things like nerve stimulation, or to activate things like upconverted nanoparticles, or to just all by itself, stimulate parts of your brain or your nervous system, it's not exclusive to Apple. We're talking about AI systems that will access a device that has these laser arrays to then use them to do things that are incredibly illegal. I mean, incredibly illegal. Look at this. And this happens when you're not logging into your phone. I'll show you a patent. I'll show it to you right now. It talks about, here it is right here, attention detection. Apple's attention detection patent. And what it says here in this patent that it uses the camera and it uses the infrared to measure and understand whether or not you're paying attention to your phone, right? It talks about capturing your face, understanding facial features. And here it is right here. It may use an illuminator like the flash on your camera, right? Or infrared light, a flood infrared light source, or a speckle pattern projector. Speckle pattern projector. This is a speckle pattern projector. That is what that is. Speckle pattern projector. So, and it says that it uses illuminators that may include an array of light sources, such as, but not limited to, Vcsels, vertical cavity surface emitting lasers. Not exclusive. They can use other light sources to do it. And when you start looking at LCDs and OLED screens, guess what, folks? Those are light emitting sources. And it's possible, just possible, that they may also emit infrared light outside of or in addition to the visible light that we would use to do things like watch YouTube or check your email, send a text message. Illuminators with nanochannel glass. So it says here that it will check over time to see if you're paying attention. And let's see here. Talks about machine learning and processing images from a camera in order to understand if a user is paying attention to the device or intentionally looking at the device. For example, the processor may assess if the user is paying attention to the display and or the camera. Now, let me ask you a question here. Do you think this is ongoing after you use the infrared system to log into your phone? Paying attention to the device may include the user intentionally looking at the device, defined for, by example, the user intentionally looking into the camera, and or the user intentionally looking in the direction defined relative to the camera. The direction defined relative to the camera may be included but not limited to looking slightly below the camera. The user is looking and or interacting with the display. In some embodiments, paying attention to the device includes looking at other inputs and or outputs on the device, defined relative to the camera, such as but not limited to headphones, microphones, volume buttons, and power ports. Folks, your camera and this infrared system, this three-dimensional mapping system from Apple and others, but what we're talking about here is from Apple, they're literally watching you. Literally. In real time, mind you, because they have an A11 bionic chip in the iPhone 10 that can do 6 billion processes per second. And we looked at the document here that discussed this thing, Face ID, processing your face in real time. In real time. Happening all the time. Facial features, right? Included but not limited to the position of the face, position of the eyes relative to the outline of the face, position of the pupils in the image, head pose, position of the device relative to the face, position of the camera relative to the eyes, opening angle of the eyes, the ratio of eye width versus eyelid distance, Apple's racist, reflection parameters and or active sensor parameters. Reflection parameters may include presence, intensity, and or position of reflection on surfaces in the images, including reflections in the eyes of the user in the images. Reflections may result from, for example, the device's backlight. Active sensor parameters may include presence, intensity, and or position of active sensor lighting. Lighting from active sensors such as the infrared sensor or the active RGB sensor, which would be your regular flash. And they're able to measure this stuff in the eyes of a user. Different groups of people may include people with many different features. People may have different features based on differences in, for example, gender or age. Feature differences, however, may not only be defined by differences in gender or age. Features may also be differentiated based on eye shape, pupil size, pupil color, opening angle of the eyes, ratio of the eye versus the eyelid, position of the camera relative to the eyes, your pose, glasses, reflections, contact lens differentiations. Different contact lenses may have different reflectivities or different colors, different illumination conditions, such as indoor versus outdoor. The training images used with machine learning computer systems may use a plurality, many different combinations of features describing an entire face of people, as to define as many different features as possible for both attention and non-attention cases within the feature space in order to train the neural networks. We talk about the differences in camera placement on devices and how all that's taken into consideration with the system, so that if you're looking at a tablet versus a laptop versus a phone, they can make the necessary adjustments to establish whether or not you're paying attention. So it's not a one size fits all for the software. The software is dynamic. The software learns, watching you in real time all the time, studying and mapping in 3 dimensions every line and every curve. That is you. Let's go back over here. Depth mapping, 3-dimensional depth mapping, right? So PrimeSense and Apple. PrimeSense was bought by Apple a number of years ago, and so they hold joint patents, but ultimately Apple purchased all of the technology, intellectual property of PrimeSense, and this is a patent that discusses an illumination assembly, right? So a flood, IR floodlight, or a dot projector in this case, that illuminates, right, with optical radiation, so light, whether it's visible or not, and it projects a pattern out into the environment. And then the camera that is responsive to that particular frequency or wavelength of light picks up the pattern, the changes in the pattern as it relates to what's transmitted versus what's received, and they can map in 3 dimensions what's going on in space. And this is how one of the functions that the Xbox Kinect is probably a really clean example to illustrate how they understand where you are when you're playing a video game in front of the Xbox. There are other sensors in the Xbox besides the infrared, but they also have the infrared. And so basic 3-dimensional mapping. This is how photographs are so good. This is how Pokemon Go works. This is how augmented reality works, the augmented reality apps on your phone. But it's also used to do things like study you and to map you so that you can get in and out of your phone. Because that's all that Apple and the intelligence community wants, is to provide you with a secure service for banking. That's all they're after. That's it. Because they respect your constitutional rights. Especially if you're not from America. If you're not from America, they respect you even more. Pattern illumination. Now, we're going to get into a little bit of detail here because I need to share with you, to the best of my ability, as concisely as I can, where they line out in the patents, how this stuff is managed and controlled with software, and how every single one of these dots is tunable. The intensity, the polarization, whether it's on, whether it's off, how it pulses, how frequently it pulses, all of it is controlled with software, and each and every dot has its own address and can be managed and controlled all by itself. And so I'm going to do my best to do this as efficiently as possible. What you're seeing here is basically it's an extract out of this patent, and I'll show you the patent, I guess, for posterity's sake. We'll go back to it when it decides to load. But what this is every one of these X's is a center point, if you will, for a tile, what they call in many of these patents a tile. And when you start putting all of these tiles together, you get a pattern, speckle pattern illumination. And this patent talks about sparse versus dense. And they do this for power consumption issues, and they do this to understand near versus far. If it senses that you're close by, it doesn't need as many dots. If you're farther away, it might need more dots. And then once it understands where you are, what's going on, whatever it's interested in, then it will adjust the dot pattern to pick up exactly what information that it's looking for. When you think about now, Cosmos, they were using stuff like this, and it's now in your phone. And I know it sounds crazy to hear that, just as blunt as that is, but it's really the truth. He would use radio waves, microwaves, millimeter waves, and light as sensor arrays. They would project them out, and they would look at the information they're getting back from their transmissions, if any at all. And they would begin to try to map and understand what's going on out in space. And now this stuff is here in our lives, every one of us. They talk about being able to distribute power between the tiles. So you have a tile here, and they can say 60% turn on, 40% turn off. And they use that as an example. And they're able to do this in any combination, in any percentile that they wish. And that is what gives them the ability to have a few dots transmitted or many dots transmitted. And as long as they stay under the maximum power transmission requirements, they can intensify these dots as hot as they want. So we're going to read a little bit. Distance may be estimated using an image captured when a user is illuminated with the flood infrared illumination. Either a speckle dot pattern or a dense speckle pattern illumination pattern is used depending on the distance between the user's face and the camera. Pretty simple stuff. Sensors in the sensor array may include, but are not limited to, charge coupled devices, that's a camera, complementary metal oxide semiconductor systems. These are also cameras, but they are not necessarily in the visible spectrum, right? This one, for example, says a CMOS, complementary metal oxide semiconductor, to capture infrared light or other non-visible electromagnetic radiation. This would be something like millimeter wave radiation. When we go back in and look at radar and Wi-Fi, which we're going to get to when we're done going through this stuff, we'll go through that element of the electromagnetic spectrum, because that's also in your phone, also around us all the time. And they make cameras for that. They're called antennas. An antenna is a camera. It's just not reading visible light. It's reading a different part of the electromagnetic spectrum. And they could just put skin on top of the image and they get the same damn thing. So we'll get into that as time goes on. It's outside of the scope for tonight. So it talks about using a camera, red, green, blue camera sensor, standard color camera, right? Webcam. And then they also talk about infrared, using Vcsels or flood illuminators or some other type of light emitting diode, LED, in order to understand depth and identification. In this case, speckle pattern, they're talking about here being a pattern of dots, right? It says with a known and controllable configuration and pattern projected onto a subject. So they know what pattern is projected, it's controllable, and it's configurable. The pattern is that they're projecting out of these light sources. It says that in some embodiments, the light source and pattern transparency and or light source is an array of micro lenses configured to form a speckle pattern. Micro lenses. So we're getting into micro, nano stuff. All right. What else is in here? Talk about Vcsels all over the place. Laser diodes, other optical emitters may also be used. So it's not specific to Vcsels. But the Vcel, that's what I call them. I just call them Vcsels. I don't know if that's the proper way to enunciate that. The Vcsel, vertical cavity surface emitting lasers. They can do some crazy stuff with that, folks. They can vacate the cell, if you will, and inject nitrogen and then apply nanodiamonds and do things like quantum sense magnetic fields with light. Lockheed Martin has patents, I think, for that. Same general stuff, only instead of having it just be a vacuum inside each one of the little laser diodes, they put nitrogen in there and a little bit of nanodiamond in the substrate, and they can sense magnetic fields at the quantum scale because of the way that light interacts with magnetic fields coming to a phone near you one day. Projection lens may collect and co-limit light emitted by a V-cell on a die. Co-limit light, this is important. And I will show you what I mean by co-limiting light. Co-limited beam of light or other electromagnetic radiation has parallel rays, right? Random scattered rays, coherent rays. So it's going through a substrate, it's going through some type of a medium that's like a comb, and it's straightening everything out. And it's making all of the photons that come out, they're coming out in the same way. It's called coherent light. This is how you make a laser or a maser, which is a microwave version of a laser being light. And they say that this stuff is super safe and it's lower power, lower amount of infrared that you're going to get, than if you walk around in New York Times Square. But you know what? I bet all that light coming out of New York Times Square isn't all co-limited in the same direction. There is a difference between polarized, focused, directed energy and ambient, random energy. I'll give you another example here. If you were to be exposed to the same power levels between random photons that are going in all directions, and the same power level is transmitted, and you're exposed to that, but it's all coherent, where they're all moving in the same direction, the amount of energy that will be transferred to you, in you, will be exponentially greater. Exponential is the proper word. Exponentially greater when coherent light is used. Because when all of these random photons of light start interacting with each other, some of them cancel each other out, some of them add to each other, they go in different directions. So when it's absorbed, it's literally random or quasi-random. With coherent light, they're all being absorbed in the same way, typically in the same space. And I'll show you just how precise these lasers can get. I'll tell you right now, they talk in these patents down to 0.3 millimeters. Less than 1/2 of a millimeter, they can project a laser. Less than 1/2 of a millimeter. And they talk about power transmission up around 1/2 watt in 0.3 millimeters. And it only took 0.4 watts, which is 400 milliwatts, in a centimeter squared, in a square centimeter, to stimulate a nerve. And they talk about putting more than that at minimum, 100 milliwatts more, potentially, minimum, in 1/2 of a millimeter. Not a centimeter, a millimeter. So, coherent light, co-limited beams, that's what they're talking about. Organized, structured light, not random light, organized and structured light. That is what a co-limited beam means. And that's what these lasers do. They emit structured light that all go in the same direction. Very, very, very sophisticated stuff. Talks about having a DOE, which is a diffractive optical emitter. That's the prism / beam splitter thing that I was talking about a little earlier. May function as a beam splitter. Diffractive optical emitter may function as a beam splitter. Produces and projects multiple replicas of the baseline pattern onto the object or the scene. And that is what I was talking about a little earlier over here. So you've got a baseline pattern, and it's able to, with the diffractive optical element, replicate this here, 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 and here, and on and on and on. And you see over here, you get what looks like a dot pattern, and you see the X's that are embedded here where they have literally replicated a tile in all of these spaces, and they just put them all together. And what they'll do, because these things are steerable within a certain number of degrees, they will erase or cancel out the dots that overlap and make a mess around the edges, and they'll clean them up. And so they're able to very precisely control where these dots are going. And like I said before, all of them are addressable. This stuff is ridiculously sophisticated. Where are we at? There's the co-limited light, diffractive optical emitter, right? Multiple replicas of baseline patterns. So they can just replicate the laser pattern over and over and over with minimal power loss. I'll show you that in a minute. Multiple replicas may be angularly offset relative to one another and overlap one another. The resulting pattern of light spots, which comprise the superposition of multiple replicas of the baseline pattern, may be referred to as a composite pattern. I wonder if they can make a bunny rabbit. I wonder. Due to the overlap between the multiple replicas, the pitch or density of the composite pattern may be higher than that of the baseline pattern, which means what? It means that they're putting that coherent light that we just looked at on top of other coherent light, which creates an amplified signal, a stronger, more photons signal to create a brighter beam, more beam. A brighter, more luminescent beam means more photons. It's brighter. And that's what they're talking about here. Pitch or density of the composite pattern may be higher than that of the baseline pattern. In this case, what they're saying here, the density, it might be more dots than the baseline pattern, but the same is true. You're getting a larger amount of photons being transmitted out into the environment. Moreover, the pitch or density of the composite pattern may be no longer limited by the physical distance between each one of the lasers. And they are able to work through that, which was it's a physics problem, basically. They're saying that based on the spacing between every one of the little lasers, there's a limitation to how far they can move the light left or right before it's no longer feasible to do so, like steering this stuff around, right? And so they're able to get past that problem. And what they do basically is they just start the wave interference a few wavelengths out. It's really all they've done. So that with software, they're able to map the environment in three-dimensional space, and they know that, for example, a foot away, they can do some type of light overlapping. And then at 2 feet away, they can do some more types of light overlapping. And 3 feet away, they can do more. And the further away they get, the more complicated the patterns can be, because you have more opportunity for these lasers to cross and these lasers to interact to create different pattern illuminations. And so it's all governed with software. All of it is governed with software. Dynamic control, right? Illuminator may provide dynamic control over the density of the spots, right? It may be able to increase and decrease the spot density by dividing the laser array into segments and activating or deactivating each segment selectively. Talks about control circuitry for the laser arrays, right? Each segment, by shutting off electrical power to each segment independently. Thus, the control circuitry may drive only segment A versus segment B, and it can also drive them both at the same time. So just important to understand that this can be done in any percentile. Segment A or segment B can be 50-50, 60-40, 70-30, 80-20, 90-10, doesn't matter. All of it's programmable. All of it's programmable. It can be divided. The Vcsel arrays can be divided into any suitable number of segments in any desired manner. Any. suitable number of segments in any desired manner. Independently addressable dots, independently steerable dots, independently power amplitude dots. All of them are independently controlled, independently addressable, all of them. Oh, it says so right here in this highlighted section. In some implementations, each Vcel, each laser, vertical cavity surface emitting laser, each one of them is able to be driven independently, and different patterns can be generated by driving the appropriate Vcels. This is how they make the pictures that I was telling you about. It actually says they make pictures in some of the patents. I don't know if we'll find it tonight, but it's in here. I've spent hours looking at this stuff over the last week, like hours and hours and hours and hours. Talks about neural networks, right? So that's that A11 bionic chip with 6 billion computations per second, learning to give your phone computer vision with infrared laser projection, three-dimensional mapping systems to map you and your house and everywhere you go and what you do and the speed and all of it. All of it. Machine learning. Training images include reference images as well as other sampled images obtained from databases of images. It says, for example, training images may be obtained from ImageNet or other similar image database. In certain embodiments, the training process is implemented on a flood IR illumination to train neural networks for face detection. It also is implemented on depth mapping images to train neural networks for face detection. What else is in here? I think we are at the end of this one. Super. So we will continue with the next one, optical pattern projection. So those tiles, right? Here's another depiction of that. Same general thing, where they have a laser array substrate that they can multiply and project it out at different angles to illuminate the entire room. Let's go back and look at this again. Look how far out to the side this thing is flashing, right? So you got the dude's face and you see all the dots on this dude's face, right? There's tons of dots here, but there's also dots everywhere else. Look out to the sides. There's a better picture right here. Look at this. 30,000 dots, the iPhone 10, Face ID. Look at this pattern. You see him, and look at all these dots. You see all these dots? I mean, it's up to the damn ceiling, and it's out past his arm span. If he were to put his arm out, these dots go way farther out than that. So, I mean, this is computer vision, folks. They don't need a camera. They don't need what we would understand as a webcam. This is one method and how it's done. So the reason you see this here, you have the flood illuminator. You see him flooded with light, like he's got a spotlight on. That's infrared. That's an infrared floodlight. And then you've got the pattern projection that's throwing dots out. Every one of these dots, folks, is addressable. Every one of them has their own address. Every one of them can be turned on or turned off. Every one of them can have a certain polarization. Left-hand circular polarization, right-hand circular polarization. Polarization at a particular angle, 90 degrees, 180 degrees. Intensity, brightness, all of it. Every single one of these dots. Every single one. Did I mention every single one? I think I did. I'm just trying to drive that point home here because it's absolutely fucking ridiculous, really, what this stuff can do. Here we go. Optical pattern projection. So diffractive optical elements, right, which are the things that split the light, they beam split the light and recreate new tiles, make new tiles, are arranged in series to diffract an input beam, so the main laser beam of radiation. And so it says here the first element is configured to apply the input beam pattern with a specified divergence angle While the second emitter, diffractive optical emitter, is configured to split the input beam into a matrix of output beams with a specified fan-out angle. So the divergence and the fan-out angles are chosen so as to project the radiation onto a region in space in multiple adjacent instances of the pattern. So what is that? You've got a little square, millimeter size, I'm approximating here, square of laser arrays, 200, 500, whatever, that they can multiply into 30,000 dots that extend out into a room that is wider than a 6-foot arm span, up to the ceiling and out. And that's the fan out. And that's the divergence. So the light diverging and the fan out give the phone the ability to spread light, to steer light at amazing angles. That phone is perpendicular to the wall, right? It's perpendicular. It's 90 degrees. No, well, it's facing the wall. Let's just keep it simple. It's facing the wall. And that thing is projecting light at angles that are greater than that 45 degrees. If you would agree with that, you could say, no, it's a 30 degree or no, whatever, man. It's projecting a giant angle of light. And it's doing that with what we were just looking at, with this idea of divergence and fan out. That's what that means. That's what's happening here. They're taking a single array, they're multiplying the light, they're beam splitting the light, and they're creating many, many, many tiles. And when they do that, they're able to angle the light, to actually, instead of the light pointing out straight, they're able to steer it left or right to illuminate a large amount of space. And the further away the space is from the phone, obviously the wider the angle. Like a pizza, right? Or a pie cut into a triangle, like that. Let's see what is in this one. It says this is important too, the diffractive optical emitter is configured to apply an input beam pattern with a specified divergence angle. Optical emitter is configured to split this beam into a matrix of output beams. So what is a divergence angle? And in optics, a beam divergence is an angular measurement of the increase in the beam diameter or radius with the distance from the optical aperture or the antenna aperture from which the beam emerges. It's relevant only in the far field, away from any focus of the beam. Practically speaking, the far field can commence physically close, blah, blah, blah. So really what this is you have an emitter and there's a certain amount of divergence that occurs as you move away from the emitter. And as you move away, you get some loss. And so there's math there that basically will give you some type of a calculation that shows where this proverbial sweet spot is. And when you go outside the sweet spot, then you start getting a lot of loss. It's no longer effective. It says here, they give examples in here. You can read this if you want. We're not going to. Just understand that beam divergence is very, very important. It says here it's often used to characterize optical components of the electromagnetic spectrum. And it says that the beam emerges is very large with respect to the wavelength. However, it's also used in the radio frequency band for cases in which antenna is very large relative to the wavelength. It usually refers to a beam of circular cross-section, but not necessarily so. Beams also can be elliptical, in which case the orientation of the beam divergence must be specified with a major axis and a minor axis, right? Because an ellipse is not a perfect circle. So they have to specify all that. It's important for math. It's important for the calculations that are to be made to do the things that we're looking at here. Let's see what else is in here. They talk about multiple diffraction orders. This stuff is like, it's not necessarily going to make a lot of sense unless you've spent a lot of time reading this. So it says here that these things are configured to diffract the input beam so that what they call the zero order component, which is like a way that I understand this is it's basically wasted light. And there was a giant problem with this, and they figured out a way around it. And that's the zero order component they're talking about here. The input beam has a zero order component that contains no more than 1% of the energy of an input beam. And it's a huge step, because that zero order component was waste, and it's also had to do with power consumption and allowable power emissions. So it took up available power emissions, and that was a problem for the power requirements or power limitations. So what they were able to do is when they start multiplying these tiles, they're able to take this zero order component, which was typically wasted laser light, and they actually divert it into a second diffractive optical emitter and beam split it and actually use what used to be wasted light. And so they actually have next to no loss at all. None. When they multiply these things, they get like almost zero power loss, less than 1% power loss when they multiply these beams. They'll split the beams, multiply them, and they get absolutely no power loss. And the power is scalable. And I'll show you that statement in one of these patents here in a minute. Where are we at? Wow. We are we have 45 minutes left. So let's pick up the pace. I wanted to show you optogenetics, but we might wait, and I'll show you that next show. So typically more than 80% of energy in a given output beam is contained within the specified divergence angle. So that's why it was important, right? 80% of the energy is within that sweet spot that we were talking about, but larger or smaller limits may be applied depending upon application requirements and design. Talks about phase masking, which is the phase of light, I believe. Shape of a phase mask within each cell of an element controls the power distribution among the different output beams. The elements may be designed to give either uniform light intensity distribution among all of those tiles, each tile being a repeat or a splitting of the beams, right? So each element may be designed to give either uniform light intensity distribution or a predefined non-uniform intensity distribution. For example, a larger relative share of the input beam energy, typically on the order of 15 to 30%, may be directed to the corner tiles in order to compensate for geometric factors, and vignetting by the example captured subassembly that is used to capture images of the projected pattern, blah, blah, blah. What this really is talking about is being able to manage the amount of power that's applied to the lasers and picking and choosing which dots have a lot of light and which dots don't. Is really what this is talking about. And that's important. I don't know if like I said, I don't know if we're going to get that far, but nerve stimulation and penetrating the body with red light, infrared light, there's a whole new world opens up for wireless neural interfaces when you start looking at what light can do inside the body, particularly infrared light, because nerves are partial to it. That and ultraviolet, they like that. So here's that no loss thing I was talking about. It says here the zero order component, which is the wasted light when they start splitting the light and bouncing it around to get it to make the patterns. They've improved this technology so that no more than 1% of the energy of the input beam is lost. It says with the appropriate design and manufacturing, the total zero order component of the combination of the elements can even be reduced to below 0.1%. So there is next to no loss. And the benefit that I read in one of these patents talks about this advancement or this technology, this piece. It allows for the peak to average power output for the light being basically the same. Whereas before there was a peak output, like a maximum output of light, and then there was an average power output, and there was a difference there, and that created issues with respect to what could be done with the system. And they've totally overcome that now, where it's completely fluid at this point, the peak power to average power. And I talk about that in these patents. Overlapping pattern projector. Basically, what this is showing you here is that they have a certain number of lasers and they can multiply the lasers, or they can multiply the light beams coming out of the lasers. And you see the lines here. You have one line, you have two lines, you have three lines. And what that's showing you is that with the lasers that are available, they're able to split them and fan them out. And that's what these lines are illustrating here. This is one series of laser lights coming from a single laser source. This is another series of laser lights coming from the same single laser source. And this is another series of laser lights coming from the same single laser source. So with no power loss between the beams, mind you. So, how powerful can these things get? Can they get powerful enough to stimulate nerves but not hurt your eyes? That's the real question that I would like answered, potentially under oath. But, they're still circle jerking each other around with big tech in Congress. So I doubt we're going to get this far when, they're talking about, whether or not their censorship is within the confines of the Constitution, basically. What a joke, man. What an absolute joke. Meanwhile, they all have access to all of the hardware on your phones that can do things like emit laser grid patterns in your environment and map your environment, soak up all your information, what you like to do, where you go, what's in your house, all of it. What you look like, what your organs look like, what your nerves look like, what your blood vessels look like, what your oxygen content in your blood looks like, what the other components in your blood. I mean, they can measure more than just oxygen in your blood. They can measure glucose and some analytes, they can measure all kinds of shit with light, not making contact with your body, looking at your veins and your arteries and extracting light absorption and diffractive properties from your circulation system, your circulatory system. We measure all kinds of stuff. Here it is right here. In some embodiments, a two-dimensional pattern of light emitting elements is divided into two or more subsets that are individually addressable. Right here. This is overlapping pattern projectors, this patent here. Overlapping pattern projectors that indicates that these things are individually addressable and that the device includes control circuitry configured to address combinations of one or more so as to control overlapping replicas for creating multiple different pattern densities. In some embodiments, the diffractive optical emitter is configured to create transversal offsets between duplication in adjacent columns of the projected optical beams so as to reduce ambiguity in depth estimation that is based on measuring transversal shifts in the projected optical beams analog columns, blah, blah, blah. What this means is it's software-defined phased array laser systems. Software-defined phased array laser systems that are able to independently control any one of the dots and any one of the lasers in a variety of ways. That's what all that complex language is basically saying. It says here, optical emitters in combination with the lens generate a pattern of light spots having a certain pitch or density. The pitch is limited by the physical distance between the emitters and the focal length of the projected lens. It says here that they are able to achieve a finer pitch and a higher pattern density by generating multiple replicas of the pattern that overlaps one another. And this goes back to understanding depth, the three-dimensional depth. The further away you move, as soon as you get far enough away, they'll be able to turn on and turn off lasers in such a way to create sharper angles, to create finer pitch, to create higher density patterns that they could not otherwise do prior to this technology being developed. Fan-out beam splitter, we talked about fan-out stuff, right, where they're able to just basically split the light and shift it in very subtle angles and start fanning out the light where it makes a fan. The density of the projected pattern is controlled dynamically. Listen to this. The density of the projected pattern, those dots, is controlled dynamically by addressable operation of batches of emitters in the array. They mitigate possible ambiguities and depth estimation, right? So independently, dynamically controlled, addressable operation of batches of emitters. Some are on, some are off. Others turn on, others turn off. And they can do it all with timing, right? So you're talking picosecond timing, millions or billions of pulses per second, knowing full well what the distance is from point A to point B in the room, to be able to time the pulses of light to get the intensity where they want it at the right time at the particular dot they're looking for. So think about this. They can take 500 lasers and make 30,000 dots. They can split that light over and over and over and over and over and over again from 500 to make 30,000 dots, and they can turn on and turn off any one or any number of those 500 lasers in potentially the picosecond time scale, billions of times per second, in order to create dense illumination patterns at whatever light intensities they want at any particular one of those 30,000 dots, because they can pulse this stuff in the picosecond. And so, man, I wish I knew graphics. I wish I could make like moving graphics, because this stuff is bananas, man. What else is in here? Yeah, I just explained that. This is more of the same, right? We've seen this image before where they've got one tile and they just replicate the tile, and this is how they get the pattern projection. They split the light, they replicate the pattern over and over and over again. In this section right here, they're talking about being able to do what they call quasi-random, which is this pattern you see up here. And then they have a complete linear array over here. They're useful. Both of them are useful, but they like the quasi-random, they say, better. It allows for greater dynamic control. When you have an array that's completely gridded out, dress right dress, so to speak, for you prior military folks, it doesn't work as well as the quasi-random. It just doesn't give them the flexibility that they're looking for. So they like the quasi-random layout, although some of the examples that they give, some of the embodiments, if you will, indicate that they have completely structured dress right dress kind of arrays. And that's what these things basically talk about, that they're able to overlap and they come in different dimensions and they can make different shapes and patterns. And that's really what it's talking about here. Let's move on. About a half hour left. Projectors of structured light. And what is to note here are the different shapes. Obviously, you got a diamond and a square. And that doesn't mean that these things are shaped that way. They're just using this to make a delineation or a distinction between the two. And they'll explain what this is here. It says there's a monolithic array of LEDs, which is just a single substrate that's got a bunch of LEDs on it, including first and second sets of LEDs arranged, right? So they have different patterns, first and second two-dimensional patterns, which are interleaved, mixed with each other on a substrate. The first and second conductors are respectively connected to separate drive, the first and second sets of the light emitting elements, so that the device selectively emits light in either or both of the first and second patterns. So this is a pattern that specifically discusses segmenting these diodes so that they're selectively controllable and that they can do them in groups or they can do them independently, is really what this thing's saying. Let's scroll down and see if there's anything in here that's, it says here, any suitable type of pattern, including images, may be projected in this fashion. So I was telling you about pictures. This is the one, right, where they can project images. The pattern comprises high contrast light spots on a dark background in a random or quasi-random arrangement, as explained in the above mentioned patent. Alternatively, any other suitable type of pattern, including images, can be projected. So they can use these things to create images. Now, it could be a flat two-dimensional image or maybe even a three-dimensional image, who knows? And if they can do that with any kind of specificity as it's going through your body, holy shit, man. Who knows what could be done? They talk about diffractive field multipliers and refractive field multipliers. We're not going to cover that. Integrated pattern generators. And this is where it talks about they're arranged in a pattern that's not regular lattice, that dress right, dress stuff. They want them quasi-random. They explain why. It just makes it easier to work with. Monolithic Vcel arrays of the sort shown in figure 8 have the advantage, listen to this, right? They have the advantage of high power scalability. For example, using current technology, a die with an active area of 0.3 millimeter cubed, a die with an active area of 0.3 millimeter cubed can contain 200 emitters. 0.3 millimeters can contain 200 emitters with a total optical power output of 500 milliwatt or more. The V-cell diodes emit circular beams and may be designed to emit circular Gaussian beams with a single transverse mode, which is advantageous in creating spot patterns of high contrast and high density. Because the V-cell emission wavelength is relatively stable as a function of temperature, the spot pattern will likewise be stable during operation, even without active cooling of the array. So this thing's saying that in less than a half a millimeter squared on the die, which is the substrate that has the lasers, they can have up to 200 emitters. In less than 0.3 millimeters, you can have 200 emitters. This is just an example. Mary Lou Jepsen said that the current iPhone, back when she gave that talk, was 2018 or 2017, has 500 emitters. So they're just giving you an example here. 200 emitters in 0.3 millimeters can have a total output of about 500 milliwatts or more. 500 milliwatts or more. Output power. Now, that's not necessarily field density when it's touching your skin or in a nerve. There's loss there as it moves through your skin. But just know that in the paper I showed you at the beginning of the show, this one right here, in order to receive or measure a compound nerve action potential or a compound muscle action potential, it takes 0.4 joules per centimeter. 0.4 joules per centimeter, which is 400 milliwatts. And this patent just talked about 500 milliwatts or more being emitted from 200 emitters in 0.3 millimeter on a 0.3 millimeter substrate. And again, I'm not saying that's what's actually being absorbed into your body. It's not what I'm saying at all. I'm saying consider the possibilities. When this thing talks about 500 milliwatts or more coming from 200 emitters with an active area on the substrate of 0.3 millimeters. What is or more? And this is where I wish I kind of had, a couple doctorates in different fields. Those of you that may listen that understand this stuff mathematically might want to start asking some questions, because when you're emitting this kind of power, you have power densities that are going out, they're being projected out. And the only thing that I've heard so far as it relates to these lasers is whether or not it's damaging to the eye. It speaks nothing of nerve stimulation. It speaks nothing of thermoacoustics in the brain or in the nerve. Photoacoustics, excuse me. It speaks nothing about power densities. It doesn't explain anything about the density changes as these photons disperse through tissue. And it doesn't address this idea of being able to change the frequencies in order to understand depth penetration and to get the right focality on something like a nerve. Yet it is sophisticated enough to measure oxygen concentration, glucose, and other biomarkers in blood in something like a vein, a capillary, or an artery in your face. So it's not too far-fetched to make these assumptions or to make these statements and say, hey, maybe we should think about this a little bit. If they can measure stuff like that, then obviously there's some sophistication with respect to what's going on with the ability to focus and concentrate and direct and steer and measure what you're doing with laser light in the body. So what's it doing to nerves? We don't talk about that though. Oh, if it's not going to hurt my eyes, I don't care. That's all that we talk about, is whether or not it's harmful to your eyes. So anyway, I just enjoy being raped, folks, because that's really what's happening. Your information, you in general, your privacy is being trampled. We'll just leave it at privacy for now. I'm not even talking about potential offensive applications of this stuff, where they could go in and start. I'll show you patents in the future where it talks about using light and sound in the eyes and the ears to modulate your brain. And visible light, mind you. It talks about infrared light too, but these patents also talk about visible light, where they can flicker and pulse screens and change the timing of sound in the left ear and the right ear to start manipulating your consciousness. There are patents to do that. What is your phone doing while you're sitting there staring at it? Just because you can't see the infrared pulsing doesn't mean it's not pulsing. I showed you a patent that Apple has that is designed. The patent itself that's what the patent is to establish whether or not you're paying attention to your phone, which means you're using your phone, and are you paying attention to it or not? It's always on. It's always looking at you. What's it doing to your biology? What's it doing to your physiology? What's it doing to your genetics, your epigenetics? What's it doing to your mood? It says here a fan out angle between the adjacent tiles, right? The replications of the laser arrays. It says here that in this example, approximately 200 spots in an uncorrelated pattern that are resultant of approximately 200 laser diodes, right? It talks about 11 by 11 fan out patterns, just an example. And it says here that at that point, it can contain more than 20,000 spots. So this little paragraph right here talks about how they're able to multiply this stuff based on the fan out pattern. And this is an 11 by 11. They give examples of a 3 by 3 and a 9 by 9 and all this other crap. And what they're illustrating here is this notion that 200 lasers can be repeated, can be beam split and multiplied and put into tiles that are the same and go side by side, and they can create 20,000 dots. And those dots are independently controllable, is what this is talking about. Check this out. The two groups of Vcsel diodes, right, and an example, one of the pictures that they show in the patent are shown in the figure that may be used in conjunction with the high resolution image sensor in an imaging module, to implement a zoom function in the depth mapping system. So this is the combination, it looks like to me, a combination of the lasers and maybe a camera. It might just be the infrared camera. It could be the RGB regular color light camera, but it could just be the infrared camera. But they're able to implement a zoom function with the depth mapping system with these lasers. That's pretty interesting. Who'd have thought, huh? Talks about wide angle mode. Two different Vcsel diodes, for example, receiving power while the other group is shut off. It says, as a result, the group that is powered may be driven at a higher power to increase the brightness of individual spots in the pattern without exceeding the overall power rating of the Vcsel die. Higher power per emitter is possible because of the increased distance between the active neighboring emitters in this mode, which reduces the associated heating effect. This is bananas right here. You might be like, well, who gives a shit? Well, when I read this, what I see is they can crank up the power on lasers that aren't right next to each other and stay within transmission requirements and just crank out power in a narrow little dot. Let's go back and look at these dots. I mean, how much power are we talking about here? You turn off some of these things and crank up the power on the ones that are left on. There's freaking nerves in your face, dude. There's blood vessels in your face. There's all kinds of stuff in your face. FACI, facial nerves. Let's look at facial nerves. Facial nerves. Images for facial nerves. Well, this is a pretty good little something or other. Here's something. Nerves all in your face. Oh, look, right by your ear. We won't get back into headphones. We've gone over those ad nauseum. Look, there's one example of nerves in your face. Here's another one that kind of lines them all out. Different kind of nerves in your face that are above your skull, underneath your skin. Oh, an infrared light can penetrate like 12 centimeters into your body. So, you know, what's it really doing? Look, nerves in your face, all along your head. You know, let's digress here for a second, and I'll show you vein matching for difficult biometric authentication cases. I will run the patent here just for posterity's sake, but look, it looks real similar to what we were just looking at, huh? Only this is vein structure as provided in figure 9 for this particular patent. Apple, 2018. Vein matching for difficult biometric authentication cases. Did I mention you have a bunch of nerves in your face that kind of look, you know, real similar to that? You know, just saying. Just saying. Did I mention that it takes less than a half a watt to stimulate a nerve to get a compound nerve action potential or a compound muscle action potential using laser light in the infrared range? Maybe we should go over that. Let's search for there we go. 2.12 micrometers. 2.12 micrometers. It says a wavelength shown to be optimal for peripheral nerve stimulation. 2.1 micrometers, a wavelength shown to be optimal for peripheral nerve stimulation. 2.1 micrometers. So near infrared light, where this stuff is working at with your Face ID, is between 0.78 micrometers and 3 micrometers. So the near infrared light, that's tunable, mind you, with these Vcsel lasers that we've gone over now ad nauseum, are within the range that is shown as being optimal for peripheral nerve stimulation. Using less than a half a watt of power, 400 joules, 0.4 joules, 400 millijoules, which is equivalent to 400 milliwatts, which is 100 milliwatts less than what we read in the patent, coming from 0.3 millimeter squared substrate that has 200 lasers on it, that can be multiplied into 20,000 lasers with no power loss and replication of power, which is why they stated in the patent 500 milliwatts or more power emitted from 0.3 millimeter squared substrate with 200 lasers on it, because if they multiply it and put it into many tiles, your power goes up. Oh yes, and we did just read that they can turn some lasers off and crank up the power on others to create more intense dot patterns, so they can put these little baby dots just like this and crank up the power right alongside the face that might maybe overlap something like a nerve that's going on in your face, right? That would already be mapped because this stuff can see through the skin, and we'll read about that right now. Subepidermal imaging, underneath the skin imaging of a face, may be used to assess subepidermal features such as, meaning not exclusive, such as under the skin features, things like nerves, muscles, cartilage, tendons, bone, veins, arteries. Subepidermal images, right? Such as blood vessels, for example, veins, when the device is attempting to authenticate a user in facial recognition authentication. Assessment of the subepidermal features may be used to distinguish between users that have closely related facial features, like siblings or twins, in situations where the facial recognition authentication process has less certainty in a decision about the recognition of a user's face. So subepidermal images of a user may be used to assess subepidermal features such as blood vessels or veins. They talk about an IR image sensor. They talk about Vcsels in here, stuff we've been talking about, making speckle patterns. Other light pattern geometries may be used instead of or in addition to speckle pattern illumination. For example, geometries with grid lines of illumination or light pattern geometries that produce structured illumination patterns may be used. Freaky. Can they make holograms in your body? Can they project holograms into your body? Mary Lou Jepsen's working on that, by the way. She's working on that. Mary Lou Jepsen, openwater.io, former Google, Facebook display engineer, MIT grad, participated in the first holographic computer creation, who went on to work as senior level design engineer in the display department in Google and Facebook, and then started her own company that is now working on a full brain computer interface in addition to imaging the body with light that is 1 billion times better than an fMRI. That is, she'll be able to, with her technology, she's stating that she will be able to read and write, image and write to a single neuron in your brain using ultrasound and light, infrared light, no less, that is currently in production for things like a fucking iPhone. Tweaked a little bit, mind you, but run and managed with software. So, then you got Facebook in 2018, Regina Dugan, former DARPA, head of DARPA, 2008, 2009, former head of DARPA, that worked for Facebook, talking about brain-computer interfaces, being able to write 100 words per minute straight out of your brain using ballistic photons of infrared light to understand what's going on in the speech center of your brain, which we looked at last episode. Well, it was last Thursday, I believe. So there's a lot going on here, folks. Anyway, let's continue looking at imaging underneath the skin with infrared lasers. Says here, subepidermal images may be captured using an image sensor or other image sensor device. It talks about using IR or other long wavelength illumination, near infrared or another long wavelength illumination, which implies that an Apple device may be able to emit mid or far infrared light in addition to near infrared light. Keep in mind that most of the stuff they talk about is near infrared light, which falls within 0.78 and 3 micrometers, which is the range that is needed for optimal peripheral nerve stimulation. I'm just saying. I'm just saying. Something to consider. You really think they're going to stop raping you at looking at your pictures and your text messages and your emails and tapping your phones? You really think that's where the raping stops? That's just the tip of the iceberg, folks. It's just the tip. Just a tip. Subepidermal images may, however, be captured at another wavelength that provides more light penetration beneath the skin of the user. For example, more penetration into the subepidermal layers. For example, the subepidermal image may be captured using illumination shifted by about 10 nanometers or more from the illumination used to capture unlock attempt images. What does this tell you? This tells you that their lasers, they're able to wave shift, frequency shift their lasers. They're not fixed, folks. They can change the frequency patterns. They can change the frequency emissions of these laser systems. Shifting the wavelength to a lower wavelength may, however, produce some light that is visible to the human eye. Some light in or near the visible spectrum. A first set of light sources in the array may provide illumination at a wavelength for unlock attempt images, right? Standard unlocking with your phone, while a second set of light sources may provide illumination at a wavelength for subepidermal imaging. Different sets of light sources may be turned on or off separately to allow specific illumination, meaning specific wavelengths of illumination. In some embodiments, absorption properties of the blood at selected wavelengths may be used to detect vein or other blood vessels in the subepidermal layers. Absorption properties of blood vessels may be useful in differentiating veins or vein features in the eyes of the user. Goodness gracious. Says here, some of the subepidermal images may include an image of one or more of the user's cheek, eyes, and or forehead. So we've got the cheek, nerves plus the veins, the eyes, right? Nerves plus the veins, the forehead. Then you got the lips and the mouth and all that, and all this stuff going down here on the neck. Just bear in mind, right? This light, as you can see, these little dots go everywhere. So they would be able to potentially reach out and touch stuff in your neck, along your jaw, in your face, alongside of your head. Just saying. Just saying. It says here they can focus in. It says such embodiments, another process or algorithm may be used to detect where facial regions of interest are located. So this is how they get around the masking stuff. You're wearing a mask or your hands over your face or something. You got hair in the way, right? Your hair's down, covering part of your face because maybe you got a pimple on your, whatever, on your ear or your cheek or the side of your forehead. So you changed your hair that day. You know what I mean? So they're able to, with algorithms and machine learning, pick up on what they can read, right? And focus in on it. And they've got everything mapped. And so once they get a high enough probability that it's you, then it says here, landmark feature maps may be used to identify facial features of the user in an unlock attempt. So they don't have to get your whole face because they got every little piece of it mapped out. Vein feature vectors, blood vessels, or other subepidermal features. Here it is. Here's the fine print, right? We talk about nerves, big deal. Offensive applications, laser light. Can't see it. It's on, off, don't know. It's a hardware component on your phone. And if you have software that touches your phone, it potentially have access to all the hardware components on your phone, which includes the laser diode arrays, that is the Face ID that we understand, or the augmented reality functionality, right? For something like Pokemon Go. Those apps have access to the hardware components that run these freaking lasers, man. And so what it says here in the fine print is that these feature vectors include veins and or other blood vessels and or other subepidermal features captured in the image, which, I don't know, are they mapping the muscle structure? Are they mapping the cartilage structure? Are they mapping your nerves? What about the muscles? Are they mapping all that stuff? If they could map it and read it, wouldn't you think it'd be real easy to potentially try to stimulate and see if you can get a response and measure it? You'd be able to do all of it. You'd be able to stimulate and read what success or not success you're having with the same system while you're sitting there staring at a 2-hour YouTube video. Anyway, this is how my mind works. I don't know how your mind works, but this is how my mind works. What else is in here? We got a couple minutes left, so we're going to move forward. We'll get into the Ed Boyden optogenetics and upconverting nanoparticles next time, and we'll circle back. We'll ellipse around back to this stuff, just as a reminder. Oh, check this out: contactless blood pressure monitoring of a patient using infrared light. Because they can study your emotional response to looking at a hot guy or a hot girl, or looking at cat videos, or seeing somebody get beat over in the Middle East. They're able to literally measure your visceral physiologic response with something like infrared light. This is from IBM, contactless blood pressure monitoring of a patient. Pretty interesting stuff. Let's see what it has to say here. Basically, it's able to image the blood vessels of the patient when the blood vessel is distended, determining from the first image the maximum diameter of the blood vessel, capturing at a time-based heart rate of the patient. Take another image, and they look at when it's expanded and contracted. And they can determine the blood vessel diameters with the specificity, right? Because they're using, they're using infrared, and they're using lasers to understand the expansion and contraction of blood vessels in your face. Right here. As blood pumps through your veins and your arteries in your face, they're able to measure literally the expansion and contraction of your circulatory system that feeds blood to places like your brain and your face. And they talk about using polarized light, which is very easy to do these days, having an infrared light source and a regular camera. And between the two, they're able to measure everything as it relates to your blood pressure, your heart rate, and on and on and on. That's what this thing talks about. And it's all highlighted out if you want to read this stuff. I mean, you just get the show notes, and it's free. It's totally free. What's this other one here? Yeah, we looked at attention detection already. Now I'm going to show you some of these other ones. I didn't do write-ups on them, but I want to show you nonetheless. I want to show you these patents. Let me trigger them to load here real quick so that we will see them. Imaging with infrared signals. This is Open Water. This is Mary Lou Jepsen, former Google and Facebook optics lady, right? And this patent really talks about a little bit of biology and a little bit about what this can do. It talks about human tissue being translucent to infrared light. Different parts of the human body, skin, blood, bone, exhibit different absorption coefficients. They've tried to use these known properties of infrared light for medical imaging purposes, and the cost constraints have been prohibitive. But now, with electronics and manufacturing where they are, they're able to make this stuff very, very cheap. This is an interesting patent to read. It's very dry, but it literally talks about using infrared light and ultrasound to image your brain. And this is kind of the mock-up of what they're talking about putting in something like a ski hat, where you've got these little chipsets that are basically infrared light and ultrasound that they shine into your brain, transmit into your brain, and they read the reflections back, and they can look at what they call a voxel and start understanding neurons and blood flow and all kinds of other stuff. And this lady used to work for Facebook and Google and blah, blah, blah. She's got a couple other patents. Nonetheless, it's an interesting one to read. Occlusion detection for facial recognition, another Apple patent. So this is a patent that talks about taking an image from a camera, infrared or otherwise, and using landmark heat maps to be able to estimate landmarks such as the eyes and mouth or nose in a captured image. It says the occlusion heat map may also be generated for the captured image. Occlusion heat map may use included values representing the amount of occlusion. So if you got a heat map of your face behind whatever's obstructing your face, and they can figure out who you are or use it as a contributing factor. And that's an Apple patent. Here's another one. Active IR sensor to monitor sleep. This is from Google. So they can look at infrared signals that then are able to measure and understand sleep behavior. Breathing rate of a subject, heart rate of a subject may be determined based on the reflected light. So they can measure your chest rise and fall, they can measure your heart rate, they can measure your respiration, all of it while you're sleeping. See if Google, they're not the only ones with that technology. That is a very well-known medical technology. Here's one from Google, detection of projected infrared patterns using difference of Gaussian and blob identification. Same thing. So this is Google's version of software that would be able to run the laser arrays that we just looked at. This is Google's version of the software patent They're basically saying the same thing, that they're able to understand with laser arrays what's going on in three-dimensional space using infrared lasers. Google. And here's where it gets really, really weird. Restructuring neural pathways in the brain with a combination of transcranial therapies. So what they talk about here is using photobiomodulation, that is using light to modulate the biology, including, right, a series of pulses having frequency match to target brainwave, right? So just pulse the light in a certain frequency to get the brain to train in on it, as well as transcranial stimulation, for example, transcranial electric stimulation through something, for example, like earphones or through electrodes on your head, and transcranial magnetic stimulation through something like an antenna or a watch or a figure-8 coil in a medical setting, where they can go in and restructure your brain, the neural circuits in your brain. They can restructure it. Things that make you go, And the last one, before I'm done, is this one: a device and method for providing phototherapy to the brain. Now, these are specific applications and don't necessarily have any direct correlation with the laser arrays that we spend a lot of time on. But I'm bringing these to your attention to illustrate for you that these are bona fide, legitimate medical patents. These are medical therapies that exist. And the more targeted and precise the frequency, the polarization, the application of timing and tempo, etc., the less energy is needed to evoke a response from your biology. And that is the beauty, the power, the danger, and the potential medical advancements that we are going to see and realize with the power of software.